In this video, we're going to discuss the concept of the galaxy, how that came to be accepted that these objects were actually full-fledged galaxies. And in taking a look at this, sorry about that, we'll take a look at the concept of the island universe. As telescopes were built and more light was gathered, people were able to see dimmer objects in the sky, and they saw these fuzzy things, these nebula. Kant in the 1700s coined the term island universe and thought that they were their own big collections of stars, galaxies, if you will. So what are some of the other discussions that came along into the 1900s? Well, there was a debate among astronomers. There was kind of a split. And Shapley and Curtis debate in 1920 did not settle the issue. They published papers and argued for a little bit. We'll see how the situation resolved scientifically towards the end of this PowerPoint. But Shapley's position was maybe more conventional, the status quo, that the nebula were small, as you see them in the telescope, and they were just inside or near the Milky Way Galaxy, and that the Milky Way Galaxy was the universe. It had everything. Curtis, on the other hand, thought the nebulae were intrinsically large and only looked small through the telescope because they were very, very far away. They were galaxies. So what about some of the reasoning about this? Well, the sketches, as telescopes were before photography, before the late 1800s, we have sketches, and some nebula start to show structures. We'll call them spiral arms now, and dark lanes in the galaxies. It didn't just look like a nebulous gas cloud or look like other gas clouds that are in our galaxy. As photography came along in the late 1800s and early 1900s, those photographs showed that there were dark lanes, similar to what the Milky Way shows from our point of view. There are patches on the sky that are darker in the band of the Milky Way. As another line of reasoning, counting the nova, the flashes of light, a star suddenly brightens but doesn't blow up, not a supernova, but the count of nova in a certain time interval. This is done for Andromeda and compared to the number of nova in the same time interval in the Milky Way. The number Andromeda was a lot larger. It was larger. So if Andromeda is part of the Milky Way, why is this one part of the Milky Way having more nova action than the rest of the Milky Way? It seemed unusual that one section of our galaxy would be active with nova and not the rest of the galaxy. Another bit of evidence in the early 1900s as spectroscopy was developed to the point where Doppler shifts could be detected. These nebulae were showing big Doppler shifts. So that's the support for the galaxy concept, the island universe concept. That's at least some of the supporting things. What about people who argued these were just nebula inside our galaxy? There was a report of a measurement or observation that one of these spiral-type nebula was moving fast enough to be noticed it was spinning. It was actually a misobservation. The galaxies, as we view them, these island universes, do not spin fast enough, or over a couple of years you would notice the galaxy has turned. But it was reported that one of these was turning, and if that was the case and the galaxy was far away and very big, the calculations show that the outer edge of this galaxy would be moving faster than the speed of light. And this is after 1905, when Einstein says nothing can move faster than the speed of light. Second consideration here, if they are like the Milky Way, if they're comparable to the Milky Way, they would have to be extremely far away in order to be seen as a small object on the sky. And astronomers at that time just had no concept of the huge distances in the universe. So they thought that the implication of a huge distance was wrong. And then there was one very bright nova, quote-unquote nova in Andromeda, and it was giving off light comparable to the whole galaxy. And if this object was in a distant galaxy, in order to appear that bright, it would have to be giving off tremendous amounts of energy that there was no explanation as to where that energy could be derived from. This is actually, this time, this 1920 is just on the edge of astronomers coming to understand nuclear fusion as an energy supply. But there was no mechanism for this huge brightening if the object was very, very far away. So to get rid of the energy problem, you make the object close, and thus being close, it doesn't have to give off as much energy to be observed to be bright. There's a connection. If an object is closer, it will look bright even with a low output of energy. So you can make a flashlight look brighter than the sun by holding it close to your eye. Don't do that. You might damage your eye, but I think you get the picture. Okay, what about some other data? Sketches, as I say, they give some hints that the nebula are not just gas and dust. There's some structure. And then photography becomes available late 1800s, early 1900s. And then especially I'm going to talk about the Cepheid variable stars. So let's take a look at some sketches. And these are from Wiki Commons. But 1845 with the Ross telescope, we get this sketch as what's now called the Whirlpool Galaxy, and you'll see that as the sketches get better and then move into the photography. But so at 1845, with a very, very large telescope, astronomers could detect some details. 1882, better telescope, better optics, and we start to see more detail in the sketch of this object. These sketches are all going to be the same object and photographs. Now a photograph, 1897, and I couldn't flip this from left to right or the words would be reversed underneath, so I chose to leave it that way. But it's the same object, it's just we're looking backwards in the orientation. And then 1919, even more structure coming out. And then very nice 2005 Hubble image of this Whirlpool Galaxy. So the data started to get better. The sketches got better as telescopes are bigger, and then especially photography, where the light could be accumulated on a photographic plate. Your eye takes a picture about every 1/8 of a second, so you can't accumulate photons, can't accumulate light and see details. But photography can do that, and CCD images. Okay, the Cepheid Star, very important. Astronomers were noticing that some stars, their light output was not constant, they were variable. So Eta Aquila and Delta Cephei, and Delta Cephei becomes the prototype for this category of star called the Cepheid Star. And it has sort of a characteristic shape of its light curve in fast rise and slower decline to dimmer light. So the dim is at the bottom of the scale, and the brighter time of the stars up here, and time's going along from left to right on the bottom axis. So that's the light curve of the Cepheid Star. 1908, Henrietta Swan Leavitt. She was examining the Large Magellanic Cloud and studying variable stars in this cloud, and she was able to find variable stars that had this light curve, this shape for the light curve. And it was important that she was studying just in this one cloud. This is a irregular galaxy near the Milky Way Galaxy, being disrupted by the Milky Way Galaxy, but all the stars she was studying were roughly the same distance from the sun. She didn't know what the distance was, but she knew that they were all about the same distance away. What she found is that there's, for these Cepheid variable stars, there's a relationship between how long it takes the star to go through its cycle of brightness, the period of its variation, that's connected to the true brightness of the star. And this becomes known now as the period luminosity relationship. The period is related to the luminosity being the true brightness of the star. So that was calibrated and becomes useful now. The parallax method of observing a nearby star apparently moving back and forth as the Earth orbits the Sun. This is only useful for stars that are relatively close to the Earth, and could not be used for the Large Magellanic Cloud, still can't. But the parallax measurements are good. They give us a nice firm trigonometric basis. You don't have to make assumptions, basis for determining the distance. But we need something that goes further away from that can be used for stars that are further away. So the reason we like the Cepheid stars is they provide the answer for this technique. If we do know the true brightness, if we know the luminosity, then we measure at the Earth the apparent brightness. That's easy to do at the telescope, to measure the apparent brightness. The true brightness, the apparent brightness, and the distance are related. So if you know the true brightness, you measure the apparent brightness, you can calculate the distance to the star. And that's where the Cepheid variables come into play. So in the 1920s, Cepheid stars were identified. Their light curves were found. And the stars are identified as Cepheids on the basis of the shape of their light curve. They were found in the nebula. And it's easy to measure the period of how long it takes to be bright, go dim, and then get back to bright. It's easy to measure that period in days. And the luminosities then could be found, the true brightness of the Cepheid stars could be found from the period luminosity graph. The distance of the Cepheids were calculated, and in these nebula, it's found that all the Cepheids in the nebula were much further away from the Sun than any other star in the Milky Way, much further away. So the island universes have distances to them that are actually much, much further than the diameter of the Milky Way. Much, much further. Of course, there's a range. It's from 10 times the diameter of the Milky Way out to thousands of times the diameter of the Milky Way, and further. But it was definitely found that these island universes, these nebula, had been called nebula, should be called island universes. They're extremely distant, and they're only small on the sky because they are distant. They're not inside the Milky Way. They're not near the Milky Way. Curtis was correct. Shapley was incorrect. These are galaxies, and a number of them are as large as the Milky Way, or even larger. Some are smaller, but that's our situation. We do have island universes. The Cepheid variable stars were able to confirm and settle the debate as to what was the nature of the nebula. So there's a little history of astronomy. I hope I didn't take too long, but read up on that in some other source. Would be good to review that material.